Ever get that, like, I don't know, that itch to really wrap your head around something that feels genuinely groundbreaking? Not just an incremental step, but a total game changer.
Oh, yeah.
The kind of tech that could rewrite the rules in ways we can barely even imagine.
Definitely. I think a lot of our listeners are right there with you. They want to understand those big leaps, those things that are really pushing the boundaries, but without getting bogged down in all the technical details.
Well, you've come to the right place, this deep dive. We're tackling a topic that fits that bill to a T, quantum computing.
It's mind-blowing stuff, really.
Yeah.
We've got some amazing material to work with today, stuff that really gets into the core of it all. So we'll break down the fundamental principles, the very essence of what makes quantum computing tick. And then we'll explore the incredible possibilities it opens up across a whole spectrum of scientific disciplines.
And it's not just about the science itself, right?
Absolutely not.
Our sources really highlight this intense global race that's underway,
Okay.
a strategic competition with nations vying for dominance in this field.
It's a big deal.
And of course, we can't ignore the cybersecurity challenges that quantum computing could unleash.
Very real concerns there, for sure.
So our mission, pretty straightforward, to give you a solid understanding of the core concepts of quantum computing.
That's the foundation.
We want you to come away appreciating the potential of this technology to transform industries and get a grasp on those geopolitical and security implications.
Those are crucial, no doubt.
So let's unpack this. What is quantum computing? I mean, the name itself sounds like something out of science fiction.
Yeah, it can seem a little intimidating, but let's start with what we know. Classical computers, the ones we use every day, they operate on bits, which are essentially like on-off switches. It's either a 1 or a 0.
Right, just like a light switch, either on or off.
Exactly. And when they solve problems, they do it step by step. Think of it like navigating a maze, trying each path one at a time until you find the way out.
Okay, very methodical, one possibility at a time.
Right. Now, quantum computers, they work completely differently. Their building blocks are called qubits, which stands for quantum bits. And this is where the quantum leap happens. A qubit can exist in what's called superposition.
Superposition. I'm already feeling a little lost.
Think of it this way. That light switch we talked about. In superposition, it's not just on or off. It's both simultaneously. It's like it's flickering between those states.
So it's not either, it's both at the same time.
That's the essence of it.
Yeah.
And this ability to be in multiple states at once is what gives quantum computers their potential power. Imagine, instead of trying each path in that maze one by one, a quantum computer could explore all possible paths simultaneously. It's like having a million computers working on the problem at the same time.
Whoa. So we're not just talking about speed here, are we? It's a totally different way of approaching problems.
Exactly. Our sources mention some calculations that would take today's most powerful supercomputers millions of years to complete. A quantum computer might be able to do those same calculations in just minutes.
That's not just a speed boost, it's like rewinding time.
Right. And, as Olivia Lanes, a researcher at IBM, put it, this isn't just about making existing computers better. It's an entirely new way of computing that mirrors how the universe operates at the atomic and molecular level.
Okay, so it's not just about faster spreadsheets or better AI, it's about tapping into the fundamental laws of physics.
Exactly. And that brings us to the scientific promise.
So what are some of the mind-blowing applications of this technology?
Imagine being able to simulate nature at the atomic level. Think designing new drugs, molecule by molecule, or creating entirely new materials with properties we can only dream of. Stronger, lighter, more efficient, even game-changing breakthroughs in battery technology.
It sounds almost like science fiction.
It does, doesn't it?
Mm-hmm.
But our source, Olivia Lanes, had a great analogy. She compared the advent of quantum computing to the invention of the telescope. Just like the telescope allowed us to see the universe in a completely new way, quantum computers could give us this incredible insight into the building blocks of reality.
That's a powerful comparison. But our source also mentioned that quantum computers aren't quite ready to outperform classical supercomputers in practical applications. What's the holdup?
The biggest hurdle right now is maintaining the stability of those qubits. They are incredibly sensitive to any external interference.
So even a slight change in temperature or a tiny vibration could throw things off.
Absolutely. It's like trying to balance a spinning coin on its edge. The slightest nudge will topple it over.
So what does one of these quantum computers actually look like? I have this image of a sleek, futuristic box.
Well, the reality is a bit different. Our source described the IBM quantum system 2 and its core component, the Heron chip. It's actually incredibly small, 133 qubits that can fit in the palm of your hand.
Wow, that's amazing. So much potential in such a tiny package.
But to keep those qubits stable, they need to be kept at extremely low temperatures, just a fraction of a degree above absolute zero. Colder than the cosmic microwave background radiation, which is already incredibly cold.
So this incredible technology relies on being the coldest thing in the universe. That's quite paradox.
It is, isn't it?
Now let's talk about the geopolitical dimension of this, the quantum arms race. Our sources paint a picture of intense competition, especially between the US and China.
Yes, the stakes are incredibly high. IBM, for example, is investing billions of dollars annually in quantum computing research and development. They're not just focused on building a better computer, but on creating an entire quantum industry.
And while they keep tabs on their competitors, they're drawing a line when it comes to collaboration, especially with Chinese companies.
That's right. They have a strict policy against it, citing national security concerns. This really highlights the strategic importance that governments are placing on quantum technology. It's not just about science anymore. It's about national security and global leadership.
It seems like China is pulling out all the stops in this race.
Oh, absolutely. They've invested over $15 billion, more than 3 times any other country. They have established numerous research institutes dedicated to quantum technologies and currently hold over half of all the patents in this field.
That's a significant lead. What's the US doing to keep up?
Well, they've implemented export controls to prevent the most advanced U.S. quantum technologies from being shared with China. And they've passed the CHEPS and Science Act to increase funding for research and development in critical areas like quantum computing. It's a clear sign that the U.S. is taking this competition seriously.
It sounds like we're on the verge of a technological revolution with major implications for global power dynamics.
There's no doubt about it.
But apart from the geopolitical concerns, there's also the very real threat that quantum computing poses to cybersecurity, right?
This is a huge concern. Our source explained that much of our online security, everything from banking to email, relies on encryption.
Right, those secret codes that scramble our data and keep it safe from prying eyes.
Exactly. And a common encryption method, called RSA, is based on the difficulty of factoring large prime numbers.
Right, like if you multiply 17 by 31, you get 527. That's easy. But if you only know the 527, figuring out the original numbers is a much harder problem.
Right. Now imagine those numbers being hundreds of digits long. For classical computers, factoring those massive numbers would take trillions of years, which is why this encryption method is so secure.
But quantum computers could change that, couldn't they?
Yes. Because of their ability to perform calculations simultaneously, they could potentially crack these codes in a fraction of the time. We're talking about reducing a problem that would take trillions of years to mere minutes.
That's a terrifying thought. I mean, all our sensitive data could be vulnerable overnight.
Exactly. Our source highlighted the concerns within the banking industry. Imagine what would happen if trillions of dollars worth of transactions were suddenly exposed.
It would be chaos. Identity theft, financial losses, a complete loss of trust in online systems.
And it gets even scarier. There's something called store now, decrypt later. Think about it. Malicious actors could be collecting encrypted data right now, knowing that they can crack it open later when they have access to powerful enough quantum computers.
So even our past communications, the things we think are secure today, could be vulnerable in the future.
That's the threat. It's not just about protecting data in the future, it's about protecting the data we've already generated.
This really emphasizes the need for new quantum-resistant security measures.
Absolutely. And one promising approach that our sources discussed is called quantum key distribution, or QKD.
Okay, that sounds very high-tech. How does it work?
It leverages a fundamental principle of quantum mechanics. The act of observing a quantum particle changes its state. So in QKD, they use single photons, particles of light, to generate and transmit encryption keys.
Okay, I'm following so far.
Now, if someone tries to intercept those photons to eavesdrop on the key, that very act of observation will alter the photons, making the eavesdropping attempt detectable.
It's like those alarms in stores. If you break the beam, the alarm goes off.
That's a great analogy. And because any interception is immediately detectable, the legitimate parties can abandon the compromised key and generate a new, secure one.
So it's like having an unbreakable encryption system.
In essence, yes. And Toshiba has already developed a QKD device that's being tested on existing fiber optic networks. They've successfully transmitted sensitive financial data, medical scans, and even government data across London.
So this isn't just theoretical anymore, it's being put into practice.
Exactly. And there's a real sense of urgency to develop and implement these quantum-resistant security measures.
Especially since our sources estimated that cryptographically relevant quantum computers could emerge within the next 5 to 7 years.
That's the time frame we're looking at. It's no longer a matter of if, but when. And it's not just about individual companies or banks. National security is at stake here.
Our sources highlighted other countries making significant progress in this area, like China, which launched a quantum communication satellite back in 2016 and is building a national quantum network.
Right. And Singapore is focusing on developing commercially viable, unhackable networks using nanosatellites, which are much smaller and more cost-effective than China's larger satellite.
It sounds like a global race to secure the future of communication.
You could say that.
Looking at the future of quantum computing as a whole, our sources talked about the delicate balance between international collaboration and the rising geopolitical tensions.
Absolutely. The early days of quantum computing saw a lot of collaboration between researchers and companies from different countries. But now, with the US-China rivalry intensifying, things are getting more complicated.
So, on the one hand, we have this incredible technology that could benefit all of humanity, but on the other, there's this fear that it could be used for harmful purposes.
It's a difficult situation. The U.S. has implemented export controls to protect its technological advantage, but there's a concern that these restrictions might stifle innovation.
It's a classic dilemma. How do we balance national security with the potential benefits of scientific progress?
And there are no easy answers.
It seems like the scientific community is trying to stay focused on the positive potential of quantum computing.
They are. They see it as a tool that could revolutionize medicine, material science, and our understanding of the universe.
It's like that analogy with the telescope, right?
Exactly. One of our sources, Professor Hannah Fry, made a really interesting point. She said that we should think of quantum computing not just as a race, but as the development of a powerful new scientific instrument.
So instead of focusing on who wins the race, we should focus on how we can use this tool to benefit everyone.
That's the ideal, isn't it? To use this technology for the greater good.
So, to wrap things up, we've explored how quantum computing works, its potential to revolutionize various fields, and the very real cybersecurity threats it poses. We've also discussed the geopolitical tensions surrounding this technology and the race to develop quantum-resistant security measures.
It's a lot to take in, but it's incredibly exciting and a little bit daunting at the same time.
We're on the verge of a technological revolution that could change the world as we know it.
And as quantum technology continues to evolve, we need to ask ourselves some tough questions. How do we balance national security concerns with the need for international scientific collaboration? How do we ensure that the benefits of this technology are shared equitably? And how do we protect individual privacy in a world where encryption can be broken?
It's a lot to ponder, but these are the questions we need to be asking as we enter this new era of quantum computing.
Because the choices we make today will shape the world of tomorrow.
And that's something for all of us to consider.
Absolutely. Thanks for joining us on this deep dive into the world of quantum computing.
We'll see you next time.